Welcome to the deep dive. If you're working in machine learning, especially in high-stakes fields, you know the drill, relying just on accuracy. Well, that's often not enough, right?
Absolutely not, especially in areas like medical diagnosis. We need evaluation metrics that are robust, reliable, particularly when dealing with imbalanced data sets.
Exactly. And given your expertise, in ML, data science, maths, it's not just about the metric value itself. It's about knowing how reliable that number is, quantifying the uncertainty.
That's the key. Point estimates only tell part of the story.
So today we're doing a deep dive into making one of the best metrics we have, the Matthews Correlation Coefficient, or MCC, statistically solid for multi-class problems. We're unpacking a formal framework and, crucially, how to get rigorous confidence intervals.
Yeah, this is really important work. MCC is widely recognized. Its balance performs well even with class imbalance, which studies have shown is a big advantage over, say, the F1 score sometimes.
Right.
But the problem, until recently, has been the formal side of things for multi-class scenarios. Where you have three or more classes, people use macro and micro-averaged MCC, but proper definitions and critically statistical inference methods, they've been lacking.
So our mission today is to unpack those formal definitions, look at how asymptotic confidence intervals are derived using the delta method and transformations, and see how it holds up in simulations and with real-world data.
Exactly. Moving beyond just using the numbers to understanding their statistical weight.
Okay, let's start with the basics, the notation. We're dealing with an odd-or-show times dollar confusion table, right? Where two probability of predicting class $, when the true class is $2.
And from that table, we define the usual suspects for each class I dollars. True positives, TPI, false positives, FPI, false negatives, FFNI, and true negatives, TNI. These are the building blocks.
Got it. And these build up to the binary MCC, the BIDO, that's our foundation.
That's right. It's essentially Pearson's correlation coefficient, but adapted for binary classification data. Gives us that vital make to one-to-one range.
Okay, so now the multi-class extensions. First up, macro-averaged MCC, or MAMR. How's that defined?
Manner is pretty straightforward conceptually. You calculate the binary MCC, the binary, for each of the Trado classes separately.
Right, like a one versus rest approach for each class.
Exactly. And then you just take the simple arithmetic average of all those $3 individual bino scores. That's equation 1 in the paper.
And the key implication there is that it treats every class equally, doesn't it?
Precisely. Every class contributes the same to the final man score, regardless of whether it's a majority or minority class. Very important when small classes are critical.
Okay, makes sense. Now, what about the other common one, micro-averaged MCC? Or MELI, this is the one you often see in, software libraries.
Yeah, Mellon works differently. Instead of calculating per class MCCs, it sort of pools all the per sample predictions across all classes first.
Pools them. How does that work mathematically?
Well, you aggregate the true positives, false positives, etc. across all classes before calculating a single MCC value. But here's where the paper makes a really crucial point.
Okay.
When you work through the math, the MEL formula simplifies a lot. It ends up depending only on the diagonal elements of the confusion matrix. The PI terms, the correctly classified instances.
Right, only the diagonal, so only the true positives for each class, essentially.
Basically, yes. The formula collapses to Frexum EP101. That's equation 2. And the big problem is this value is directly proportional to overall accuracy.
So it loses the very property that makes MCC valuable, the inclusion of true negatives, the correlation structure.
Exactly. It fails to provide that balanced view, especially with imbalanced data, because it ignores the correctly identified negatives. It can be overly optimistic, just like accuracy often is. Plus, it doesn't even maintain the medical and lower bound. It fundamentally breaks from the Pearson correlation concept.
That's a pretty significant critique. So if the standard MEM is flawed, what's the alternative?
The paper proposes an alternative definition, which they call MIMBLAR. This version is specifically designed to preserve that Pearson correlation structure in the microaveraging context.
How does mean achieve that?
Instead of just using the diagonal terms, MIM-Lilot equation 3 is defined using aggregated covariance and variance terms that explicitly incorporate information from all cells of the confusion matrix, TPs, TNs, FPs, FNs, aggregated appropriately.
Okay, so it keeps the spirit of the original MCC.
Correct. And interestingly, this MIM-Lilot definition turns out to be mathematically consistent with a previously proposed statistic called Swart color, developed by Gorodkin. So this work essentially provides the missing statistical inference framework for that try-the-light idea.
Right, that makes sense. So we have three metrics, MEN-FLAR, the flawed MEN-Lilot, and the correlation preserving MEN-FLAR. Now, the big step, How do we get confidence intervals for them? Statistical inference.
Okay, so all three of these MCCs, let's just call the function LFE worlds, are functions of the underlying probabilities in that Tabor table. We estimate these probabilities using the observed frequencies known from our test data.
And those estimates follow a known distribution asymptotically.
Exactly. Thanks to the central limit theorem, we know that the vector of estimated probabilities is asymptotically normally distributed.
So the first method leverages that. The delta method.
Precisely. The delta method is a standard statistical tool. If you have an asymptotically normal estimator, like our pi-fail, and a differentiable function of that estimator, like our TIFL, then the function applied to the estimator is also asymptotically normal.
And the delta method gives us the variance of that new distribution.
Yes. It tells us the asymptotic variance is calculated using the gradient of our MCC function, and the covariance matrix of the probability estimates var feeds that formula.
Okay. Once we have that variance estimate, we can build a standard walled-type confidence interval, right? Like estimate plus minus 1.96 times the standard error for a 95% CI.
That's the one. Method 1. Apply the delta method, get the variance, construct the CI. It provides the formal inference we were missing.
But there's often a complication with correlation coefficients, isn't there? Their sampling distributions can be skewed.
That's a really important point, yes. Especially when the true MCC value is close to a 1 or NIGO 1, the distribution of the sample MCC can be quite skewed, meaning it's not perfectly symmetric or bell-shaped.
And that skewness can affect the accuracy of the confidence intervals, especially with smaller sample sizes. The normal approximation might not be great yet.
Correct. The convergence to normality might be slow. This leads us to method 2, Fisher's set transformation. It's a classic technique for dealing with correlation coefficients.
Yeah, the arctan transformation. Frac 1x cotil what x?
That's the one. You apply this transformation to the estimated MCC, MAM-AM MBs, or MAM-AM. The idea is that the transformed value, FTCC day, converges to a normal distribution much faster, even with smaller samples.
So you transform the MCC estimate, calculate the CI on that transformed scale, using the delta method again for the transform function's variance.
Right, you need the variance on the transformed scale.
And then you apply the inverse transformation found out to the bounds of that interval to get the final CI back on the original MCC scale.
Exactly. It stabilizes the variance and handles the skewness, often leading to more accurate coverage probabilities, especially when ORN isn't huge.
Okay, that covers inference for a single MCC value. But what about comparing two different classifiers? That's a very common task. Paired designs.
Yes, essential. Say you have two models, X1 and Sexton 2, and you test them on the exact same data. You need to know if Sexton is statistically significantly better than X2 and 2.
This sounds like it gets much more complicated. We're not just looking at one-door times OR table anymore.
No, you're not. To capture the relationship between the two classifiers' predictions on the same instances, you need an R times R times R contingency table. The probabilities represent the chance that model sextolor predicts class Galler, model sextidolor predicts class, and the true class is O-killer.
An cube probability vector. Wow.
Yeah, the dimensionality jumps up. But the principle for the delta method extension is similar. We're interested in the difference P-cell to MCC1, MCC2. This difference is a function of that larger vector.
So we apply the delta method again, but now to this difference function, O-killer, and using the covariance matrix derived from.
Correct. And the absolutely critical part here is that the variance calculation for the difference must account for the covariance between MCCR and MCC2 and MCC-tellers. Because they were run on the same data, their results are correlated. Ignoring that correlation, that pairing would lead to incorrect, usually overestimated variance.
That makes sense. You'd lose statistical power if you treated them as independent. Okay, so the delta method works for differences. What about the transformation approach for differences? Can we just apply Fisher's Z to MCCC1, MCC2 per 10x?
Ah, good question. And the answer is no, not directly. While Fisher's Z works beautifully for a single correlation, you can't easily invert the transformation when applied to a difference of correlations to get interpretable CI bounds back on the original scale. The math doesn't work out nicely.
Right. So the standard Z transform is out for differences. What did the authors propose instead?
They developed a modified transformation method specifically for the difference. The Sale logs, they use a different function, Shapi x Shapi plus x to x.
Okay, a different log ratio function.
Yes, this function G is designed to handle the skewness of the difference distribution and accelerate its convergence to normality, similar to Fisher's Z for a single coefficient.
And crucially, this one can be inverted.
Exactly. You apply d-lawyer to the different estimate several, calculate the CI on the transform scale using the delta method for delta variance, and then apply the inverse function, g-lawyer, to the interval bounds. It gives you a valid CI for the difference back on the original scale.
Clever. Okay, so we had the theory, the methods for single MCCs and differences. How did they validate all this? Simulations.
They did extensive simulations. They used 133 classes, ran 100,000 iterations for each scenario, compared balanced data settings with highly imbalanced ones.
And varied sample size too, I assume.
Oh, yes. From quite small, $105 up to a more reasonable and $800. They tracked the empirical coverage probabilities of the 95% CIs generated by the different methods.
What were the key findings for the single MCC CIs? Did the methods work?
Broadly, yes. As the sample size $d increased, the coverage probabilities for all three metrics, minimum, min, crew, got closer and closer to the target 0.95. This confirms the asymptotic theory holds up.
Any interesting nuances? Any methods struggle under certain conditions?
Definitely. The most notable thing was with MAM under small sample sizes and high imbalance. Its coverage probability deviated quite a bit below 0.95 in those tough scenarios 3 and 4.
Why would MAM struggle more there?
Well, remember, MAM averages the per-class B-SESH scores equally. If you have a tiny minority class and only a small overall sample size, the estimate for that class's B-Lee SR can be very unstable, highly variable. Averaging in that noisy estimate pulls down the overall MAM accuracy and hurts the CI coverage.
Right. Its fairness makes it sensitive to estimation errors in small classes when data is scarce. And did Fisher transformation help?
It did, significantly. Applying Fisher's Z generally improved coverage for all metrics, pushing them closer to the nominal 95%, especially at smaller sample sizes. It particularly helped MAM, making its CIs quite reliable even when it was small.
So the takeaway is use the transformation, especially for MAM-AGLs or if you have smaller samples.
That seems to be the practical advice, yes. It provides more reliable intervals.
And the paired design simulations. Did the CIs for the differences also work as expected?
Similar story there. The coverage probabilities for the differences, MCC1, MCC22, also converged towards 95% as none grew, validating both the direct delta method approach for differences and that modified transformation method using the function.
Okay, simulations look good, but the real test is always real data, isn't it? They applied this to a medical imaging problem.
Yes, a compelling one. Comparing a faster RCNN model that's a deep learning network against board-certified dermatologists, BCDs, the task was classifying skin lesions into 6 categories, so RISHIPs or 7.
High stakes, multi-class. Exactly the kind of scenario this framework is built for. What did they find comparing the FRCNN to the dermatologist?
This is where the CIs really show their value. They calculated the difference in performance, FRCNN minus BCD, for all 3 metrics, monomonocyne, monomolosses,
And the confidence intervals for those differences.
For all 3 metrics, the 95% confidence interval for the difference had a lower bound that was clearly greater than 0.
Greater than 0, meaning?
Meaning the interval did not contain 0. For example, the man indifferent CI was 0.056, 0.122. This provides strong statistical evidence that the FRCNN performed significantly better than the board-certified dermatologists on this task.
Not just a higher point estimate, but a statistically significant difference.
Exactly. And these findings backed up earlier analyses that used the F1 score, but now with the added robustness and statistical rigor provided by the MCC framework and its CIs.
Okay, let's wrap this up. We've seen the formalization of multi-class MCC, the macro-averaged MAMA, the potentially misleading accuracy proxy MELMALA, and the correlation-preserving MELMALA.
And critically, we now have statistically sound methods, the delta method, plus the Fisher-Z and modified transformations to compute confidence intervals for these metrics, both individually and for paired comparisons.
The crucial distinction for practitioners really seems to be between MELO and the other two, right? Be very wary of MELO because it's like accuracy.
Absolutely. Maimon Level and especially Miller retain that core MCC benefit of considering the full confusion matrix, making them generally more reliable, particularly if you suspect class imbalance might be an issue.
So the bottom line is, this research allows us to move past just reporting an MCC number. We can now quantify its reliability, state with statistical confidence whether one model is truly better than another using MCC. That's a big step forward for robust evaluation.
It really is. It adds a necessary layer of statistical rigor.
So here's a final thought for you, our listeners. This work provides a fantastic framework for nominal classification, where the class labels have no inherent order. But what if you're dealing with ordinal categories? Think maybe rating scales. Mild, moderate, severe, the order matters there.
Right. Using a standard MCC metric might ignore that valuable ordinal information. So the question to ponder is, building on this foundation, what kind of modified MCC, or perhaps a different correlation-based metric altogether? And what corresponding statistical inference techniques would you need to develop to potentially gain more statistical power by explicitly incorporating that ordinal structure? That's where the next level of refinement might lie.